Hi friends, a very good evening and thank you for joining in today. Could you please confirm in the chat window if you are able to see my screen and hear to the audio? If you can confirm that, we know everything is good, no technical glitches, we can get started. So I'll wait for a couple of minutes. I try to typically join a few minutes early just so that if there is any technical glitch, we can fix it. So if everyone can hear my audio and see my screen clearly. Okay, good. So we're getting confirmation from students that everything is good. That's good to know. So we'll start the session in a couple of minutes. So just be a little patient. We'll start it. Okay, so all is good. Good. So this is the second session that we are doing for databases, and we have some more topics left that we'll do next week, right? So we'll stick to the same process of doing 2 live sessions, some publicly, some privately. Right now we are doing mostly public sessions because this is the first iteration and we are mostly covering easy and medium problems, but we'll continue to do the same till the date of exam, right? So again, we will speed up, we'll mix subjects, we'll do all of those iterations, right? So again, we have done most of other subjects. For example, we have finished data structures, algorithms, C programming. We have finished all of engineering, mathematics, theory of computation, compiler design. Now we have moved on to the system subjects, right? So we'll finish the system subjects quickly, and then we'll start the second iteration. We are hoping that we can finish the first iteration maybe by end of August if all goes well, right? With 2 sessions a week, I think we can finish the first iteration by end of August, so that then the next iterations will be faster and we'll cover more topics in each session, right? So cool. Hey, good evening folks, thank you for joining in. We'll start the session in 1 more minute, so just be patient because the scheduled time is 7 p.m. So again, let's wait for a minute or two. Again, please understand that databases is one of the very scoring subjects. The questions might be lengthy, but it's extremely scoring in the GATE exam, right? Keshav, good question. What after DBMS? We'll just announce that the coming Sunday. We're just finalizing on what subject we should cover after databases. Mostly we'll cover one of the system subjects. So we'll just let you know. Please give us a couple of days. We'll notify. Tomorrow is Sunday, so we'll decide. We typically sit on Sundays and decide what's the next subject. We'll surely announce a video on YouTube, right? Cool. So that's good to know. So it's 7 p.m. So let's get started, guys. We'll try and finish this. We have about 9 questions or 8 questions, if I'm not wrong. Most of them easy to medium, covering mostly functional dependencies, decomposition and normalization in databases. So let's get going and we can finish this in 1 hour, right? So let's move. Okay, here comes the first question. I hope it is clear. Again, for every question we tag whether it is easy, medium or hard based on GATE standard. So you can think of it as a medium level hardness problem in GATE. Again, this is a fairly simple, again, most of databases, especially with functional dependencies and related topics, if you know the concept, if you know what is a candidate key, if you know what is canonical cover, it should be straightforward to solve these problems. So as soon as a few students answer the question, I'll get into explaining the solution. This is a very typical type of problem that you could encounter in GATE. It's a very typical GATE type problem. Again, please be careful to avoid silly mistakes. Because in databases, a medium hardness question is an easy question with a little trick put in there. Okay, I see option 1 and option 2 being the popular options amongst the students, but please think through it. There is a small trick in there. I mean, the question is medium hardness because it's slightly tricky, so just be a little careful there. So yeah, I see a few answers, so let's go into the solution itself. Yeah, so at least there is one right answer now. Okay, so actually neither of them is true. So actual answer is 4, not 1 or 2. Again, we have intentionally given a tricky question because this is where people commit mistakes, right? So let me explain the solution. These are your functional dependencies. It says the possible candidate keys are OP, OS, OQ, OQR. Now obviously by just reading this you can say that how can OQ and OQR both be candidate keys? If OQ is a candidate key, then OQR becomes a super key because there is an additional attribute here. If OQR is a candidate key, then OQ cannot be a candidate key, right? By just looking at this, again, you can notice that O is not there anywhere in the RHS of any of the functional dependencies. So if you look at OP closure, just let's write OP closure. What is OP closure? You'll get O, you'll get P. From P you can get QRS, right? From QR you can also get T. Right, so obviously OP is a candidate key. O has to be there in every candidate key because O is not present anywhere in the RHS. But the tricky aspect here is how can both OQ and OQR be candidate keys? If OQ is a candidate key, OQR becomes a super key. If OQR is a candidate key, then OQ cannot be a candidate key. Right, so it's a very simple observation about candidate keys and super keys and subsets. That's the tricky part. Now let's look at the second one. Second one is where a lot of people commit mistakes. Okay, so let's look at the second part now. So if you notice here, you have P determines QRS, that is there. QR determines ST, S determines P. So here you have this additional functional dependency which is Q determines S. Right, so if you look at Q closure here, so in this set of FDs, let's look at what is Q closure. Q closure is Q comma S, and S can derive or S can generate, or sorry, S can determine. Again, this notation, the arrow mark notation is used both in compiler design and also in databases, so it's very easy to mix up the terminology, right? So S determines P, right? P will determine Q, R, S, and QR can determine T now, right? So you have Q, S, P, R, T here. While in this case, what is Q closure? If this is your set of functional dependencies, Q closure is Q alone, nothing else. Because you need both Q and R to determine S and T. Q alone will not do that, right? So obviously with just this simple observation, you can realize that 2 is also incorrect. We just saw that 1 is incorrect. So neither 1 and 2 are correct, right? So I mean, it's just about observing this simple trick and also looking at it from the perspective of Q closure. That's it, right? So it's a very common question where people will make mistakes, and that's why it is medium. Because if you know what is the definition of candidate key, if you know what is the meaning of canonical cover, this is a straightforward problem. But it is this trickiness which makes it medium hardness. Okay, sounds good. So let's go to the next question, folks. Here comes the second question. Again, it's a medium hardness, fairly simple question actually. Hey folks, I think Asif, you have just joined. Good evening and thank you for joining. Let's solve the problems, right? We are on the second problem, so you have not missed much. Again, please be careful. Look at all the 4 options that you have. Please read the 4 options. Don't just look at the first option or the second option and go into the answer. Always, this is a very common silly mistake that people commit. Please read all the options. Okay, I think most of you got it right. So it's a very straightforward problem, right? So look at this. So you have basically A determines B, C determines B, and A determines C. These are the 3 ones that you have. You also have AC determines B. But if A determines B and C determines B, you can always write that AC determines B, right? So actually both 1 and 3, both of them are correct in this case. Right, so you can either choose 1 as the right answer, because again, let me show you how to actually come to this conclusion. So A determines B. So look at all the values that you have for A. A, you have A1, A2, A3. Okay, you have B. If when A is A1, you get B2. Right, when this is A2, you get B2. When it is A3, you get B3. Cool. So given A, you can uniquely determine B. That's the whole point of a functional dependency, right? So this is surely true. Similarly, you can show that C determines B. But now let's go to A determines. So this is true. This is true. Now let's go to A determines C now, right? So let's draw it. So let's look at A determines C. So you have A1, A2, A3, right? So what do you have here? When A1 is A1, sorry, when A is A1, you have C as C1. So this is there. When A is A2, you have C3. Cool. When A is A3, you have C2. Okay, that is cool. A3, you have C3. Oh, so you have this problem. Given one value of column A, you can't uniquely determine a value in column C, because when you had A3, you have both C3 and C2. Again, it's very easy to think about it from the set notation. Even in our course videos, we try to explain this concept from a set mapping perspective, because at the end of the day, whole of relational algebra is just an extension to relations in mathematics, right? So if you think about it, A3 determines C3 is incorrect. Sorry, in other words, A determines C is incorrect. So this can't be the answer. This can't be the answer. Now you are caught between 1 and 3, right? If this was an actual GATE question paper, whether you choose 1 or 3, they would give you the marks, right? Because both are correct answers here. Right, because AC determines B is same as, I mean, you can easily derive this. If A determines B and C determines B, you can always write AC determines B. So there are some questions in GATE, even if you see it in the last few years, where 2 options are correct and they would give you marks. Again, it probably is a mistake in setting up the question, but they would give you marks whether it is this or this, right? So don't worry about it. Cool. So let's go to the next question now. Cool. Again, this is an easy question, fairly simple to solve. Again, if you know the concept of functional dependencies, this is straightforward. Again, all of these are easy questions. Intentionally, we are giving some easy questions because we want this to be the first revision for some of the students who are practicing problems. Right? There is no point directly going to medium and hard problems. We'll do that eventually. Let's start with some simple problems first. Cool. So some of you have answers, but let's wait for a few more seconds before we jump into the answers. Okay, so again, I believe Avinash just joined us. Thank you Avinash for joining in. Anyway, we are just in the third question, so you can still participate and enjoy this session and learn from it. Again, most of you got it right. I think the right answer here is 2. It's very straightforward, right? So look at this. P determines Q. For every value of P, you can uniquely determine Q, right? So obviously, so does not hold is the question. Many people make a mistake in not reading the not here, right? So this statement or this functional dependency is correct, so this can't be an answer. Now let's look at QR determines P. Now if you notice, look at this. Q and R have a value of 20, 30 here. So given a value of Q equals to 20 and R equals to 30, you can't uniquely determine P because there are 2 different values here, right? So this maps to this combination maps to this, but they are the same combination. So you can't uniquely determine P given Q and R. Hence, this is an incorrect functional dependency and hence this is the answer. Many people do not read the not part. They don't read through all the options. They'll first see this and they'll tick it. So there is a possibility of a silly mistake here, but it's a simple question. Again, intentionally we are giving some very simple questions because this is a first iteration and we want people to gain confidence slowly and steadily. Okay, so let's go to the next one. Oh, this is also a good question. This is also easy actually by gate standards. Again, you just, for this question, you just have to know the definitions of 1NF, 2NF, 3NF, Bcnf. If you know it, you can solve it trivially. Again, if you know the definitions of 1, 2, 3 and Bcnf, you can solve this in like 30 seconds. Okay, I see all answers here, 1NF, 2NF, 3NF. So just be careful. The question is, what is the highest normal form for the given set of FDs? Again, let's just assume that A, B, C, D are the only attributes that we have. Okay, I see a bunch of answers, some of them obviously incorrect, some of them certainly correct. So let's dive into the solution. Anyway, we are at it. So let's just get going. Or let me wait for a few seconds. I think some of you are still solving it. Again, you can think of it as a quick recap of definitions of 1, 2, 3 and Bcnf. Okay, so let me dive into the solution itself. Obviously, look at this. What is the property of 1NF? No multi-valued attributes, right? So no multi-valued attributes, right? So that's the whole point of 1NF, right? Again, nothing is told to us about if some of these attributes are multi-valued. So obviously it will be in 1NF. Trivial. What does the definition of 2NF say? 2NF says it has to be in 1NF and no partial dependencies, right? No partial dependencies. That's what it says. Now to compute partial dependencies, you need to know what are the candidate keys. Right? You need to know what are the candidate keys and you need to know what are prime attributes, right? So what are prime attributes? So for those of you who have forgotten what is a functional dependency, what is a partial dependency? A partial dependency is where you have a part of a candidate key. A part of a candidate key determines a non-prime attribute, right? If you just know this formula, know this definition, it's cool. Now let's write what are the candidate keys. Look at this. If you have AB, you get CD. So obviously AB is a candidate key. Obviously. Now is BC a candidate key? Yes, because if you have BC, you can get A and you can get from A you can get D. So BC is another candidate key. Again, CD is another candidate key if you think about it, because from CD you can get AB and you're done. And similarly AD, let's say if I have A and D, yes, AD is also another candidate key. Right? These are the 4 candidate keys that we have, right? What are the prime attributes? All of them, A, B, C, D are part of at least one candidate key and hence their prime attributes, right? Now, okay, look at this. Do you have so do you have part of a candidate key here, but see, what is a partial dependency? You have part of a candidate key on the LHS and you have non-prime attributes. All attributes here are prime attributes, so all of them are prime. So you can never have a non-prime attribute. So I mean, obviously there are no partial functional dependencies. Okay, so certainly this is in 2NF. Now let's go to 3NF. What is the formulation of 3NF? Anything which is in 2NF and where you have these functional dependencies where X determines Y, where X is a super key or Y is a prime attribute. Right? This is your 3NF formulation, right? Now if you notice, look at this. This is a candidate key, which means it's obviously a super key also. So this FD satisfies 3NF. This FD, this is a candidate key, satisfies. Here this satisfies this. So obviously this is in 3NF. Right? So till now what we have seen is, okay, sorry, my bad. So we have seen that these functional dependencies follow 1NF, 2NF, 3NF. Now we just have to check for Bcnf. Alright. So what is the property of Bcnf? Bcnf is you have X determines Y, where X has to be a super key. Obviously this is not true because this FD satisfies that property, this FD satisfies that property, these two FDs don't satisfy that. So obviously this is not in Bcnf, which means the highest normal form that these FDs are in is 3NF. That's it. So the reason we tagged it easy is because this is a very straightforward problem. And if you just know how to determine the candidate keys, prime attributes, and the definitions of all four of them, you can solve this in like 1 minute, right? So that's what it is. Again, we hope questions like this are good revision for you, right? Cool. Let's go to the next question now. Again, if I have moved to the other questions and there are some questions in the comment section from already covered questions, some of our mentors will try to answer them in the comment section as they join. I think some of our mentors have already answered a couple of general questions. So they'll try to answer if there is any specific question. But if something cannot be explained very briefly, please email us and we'll try to revert back to you as soon as we can. Okay, if there is any error, we'll correct it from our side. Okay, so let's see this problem. Okay, this is also simple. Yeah. Yeah, this is also a simple problem if you know how to show the equivalence of functional dependency sets. It is very important to solve a few easy questions so that your confidence levels improve and you also get into the habit of solving problems. So our recommendation always is first solve easy problems, then go to medium, at the end go to hard. That's why we are intentionally giving a few easy and mostly easier, but a few medium questions here. Okay, so let's, I think many of you have put in your answers here. So let's go into the solution itself. So you have A generates, sorry, I keep going into the compiler design terminology. A determines B, so let me write it. A determines B and B determines C here, or else I don't have to write it. See, look at this. Here A is determining B and B is determining C. Here it says A determines B, oh, but A also determines C, but B doesn't determine C. You can't derive B determines C from this. Look at this. From these two, you can create a new functional dependency which is A determines C. So from this, you can derive these two. But from these two, from A determines B, A determines C, you can't generate this functional dependency, which is B determines C. So obviously F1 and F2 are not equal. So obviously this answer is gone, right? The second thing that we have here is F2 and F3. Now let's look at F2 and F3. What does this say? A determines B, cool. Here also A determines B, okay. Here you have A determines C. Okay, so look at this. If you have A determines B and A determines C here, and here you have A determines B and you have AB determines C, right? Because A determines B, look at this, A determines B and AB determines C. From these two, you can derive that A determines C, right? So these two sets of functional dependencies are equivalent, right? Logically, think about it, right? If you're given A, I can uniquely determine B. And if you're given A, I can uniquely determine B, and given A and B, I can uniquely determine C, which means given A, I can uniquely determine C. Think about it from a set theory perspective or a mapping perspective, right? That's what is very, very helpful. Again, remember, that's why we focus so much on the mathematical foundations. This is just all about the concept of relations in discrete mathematics, right? So, okay, so this shows that F2 and F3 are equivalent. So this could be an answer, but don't jump to a conclusion. Please read the other options also. Always in the exam, please go through all the 4 options. Don't jump to conclusions. So look at F1 and F3. F1 says A determines B. So let me just clear this. So we know that this is true, but let's also, so none of the above can't be the answer. This can't be the answer, but let's just keep an eye for F1, F3. So you have A determines B. You have A determines B here also. Oh, here B alone can determine C, right? Here, sorry, it's F1 and F3, right? Yeah. So here you have A and B together determines C, right? So if you look at F1 and F3, right? If you look at F1, again, there is another way that I can argue. If you look at F1 and F3 here, right? So what do you have in B closure? Okay, so let's look at it from the closures perspective. That's another way of thinking. Here, what is B closure? B closure is B comma C here, right? So what is B closure here? The B closure here is just B itself, right? So that's another way of thinking. So F1 and F3 are also not equivalent. Again, there are many ways of thinking this, okay? We teach the approach of using the mathematical foundations of sets and mappings to explain these concepts in our course videos, because that way you're connecting the concepts in discrete mathematics to databases. There are many ways to tackle this. This is one of the ways that we find interesting. Okay, cool. So I hope everybody is convinced with this. So let's move to the next question. One second, let me just make it slightly larger. I'm sorry. Just let me increase the font size. My bad. I think mistakenly I've left it. Okay, my bad. Okay, so let's go into this. Again, please take your time. This is a very interesting, it's a very interesting question. So please be careful with this. It's very easy to make mistakes. Remember, we want it both in Bcnf and dependency preserving. Is there a problem with streaming? Let me just check. Just give me a second, folks. Yeah, my bandwidth is full cool. I mean, I'm streaming at the recommended bandwidth. If anybody has a problem, please refresh. We hope there should not be any hiccups here. Okay, everything is fine. Thanks, folks. Thank you, mentors. Okay, this question might be slightly lengthy, so please be careful. Yeah, this question is little time taking, so it's okay. Take your time, be careful, and put in your answers. Again, please read the dependency preserving part also. A lot of people just say which of these is in Bcnf and they go with the answer. Please read the dependency preserving part also. That's a very, very common mistake. Okay, I'm happy that most of you got it right. It's a little time taking, so it's okay. Take your time. I'll go into the solution in a few minutes. Okay, so most of you got it right. So let's jump into the solution. I'm happy that most of you thought through. It's a simple problem. It just requires you to be careful. Okay, the right answer is option 4, obviously. Now, again, you know the basic rules of Bcnf. First and foremost, realize that there is no B on anywhere in the RHS. So, is B a candidate key? Let's see. So, if you have B, what is B closure here? From B, you can get B, you can get E here. If you have E, you can get A. Now, if you have A, you can get D. Since you have A and B, you can get C. So, you got everything. So, B is the only candidate key. B, again, you can verify this. Try and find other candidate keys, you won't get anything, right? Anything that has both B and something else becomes a super key, right? So, the only candidate key here is B, right? That's very, very important to recognize, right? Now, again, what is dependency preserving? Dependency preserving means after you decompose into smaller relations, all of these functional dependencies must be present, or each of these functional dependencies must be present in at least one of these relations, right? So that's the important part. So let's look at this. I'll show you a couple of examples, but 4 is the answer. So if you look at this, what do you have? You have, obviously, in this you will get, okay, most importantly, look at this. You have ADC, right? You have a relation which is ADC here. In this ADC, you will get D determines C, right? You'll get this here, right? And what else will you get? You get A determines D. Okay, so let's look at this. Okay, let me write this down. For this relation, what do you get? For R2, what do you get? You have ADC and you get A determines D and D determines C. Now here D is not a super key. Okay, these two functional dependencies will fall corresponding to relation 2, right? Because they contain A, D and C, all 3 of them, right? Now if you notice, D determines C is not in Bcnf. So obviously this relation R2 is not in Bcnf. So you can completely get rid of this. This can't be the answer. Now let's look at option 2. Again, I'm trying to help you through all of them, but it's much easier to recognize that 4 is the answer. But let's see. So imagine if you see this, look at this relation 1, ABCE, right? What all functional dependencies will fall into it? You get AB determines C, because you have ABCE, AB determines C, you will get B determines E, and you get E determines A. Right? So this is what you get, isn't it? Yeah. So you get AB determines E. Yeah. So you get all of this. Cool. Now, is this in Bcnf? Oh, most importantly, B determines E is there. 1 second. Let me just think. A determines ADC. So AD. Okay. So look at this. So what do you have here? AB determines C, B determines E, E determines A. Now, obviously, this FD, I mean, given this relation ABCE and these functional dependencies, this does not satisfy the Bcnf requirement. So this is gone. Again, for third option, each of these relations will satisfy the Bcnf. So this decomposition is in Bcnf, but it's not it's not dependency preserving, because in none of this you can put A determines D. You have A determines D here, right? Because AD is not there in any of the relations. AD is not there anywhere. So this also can't be the answer, right? So again, dependency preserving is much more easy to test, right? It's much more easy to test than again, even Bcnf is very easy to test. You just have to be more patient, and for each relation you have to write down what are the functional dependencies, what is the candidate key. You have to do all of that, right? But by just looking at this, you can clearly say that this satisfies the dependency preserving, and this is also in Bcnf. So 4 becomes the answer, right? It's simple. If you know the definitions, it's fairly simple to figure it out. Okay, cool. So let's go to the next question now. Again, this is an easy question. You just have to know the definition of lossless and dependency preserving. This is a simple question. Okay, I think most of you got it right. So option 1 is the right answer. And it's very simple to see. Look at this. You have these 4 relations. You have ABC. For ABC, what will you get? You'll get this AB determines C. This is the FD that will go corresponding to this relation. Then you have ADE, right? You have ADE determines F goes here, and you have FG. So F determines G goes here, right? Obviously, it's surely dependency preserving because each of these dependencies have gone into one of the relations. So this can't be the answer. This can't be the answer. Okay. Now, if you notice, this decomposition was done keeping Bcnf in mind. You can also verify. You can verify that this relation with these functional dependencies is in Bcnf. This is in Bcnf. This is in Bcnf. This is in Bcnf. Bcnf automatically means lossless, right? That's the only catch here. You just have to know what is the definition of dependency preserving and the fact that Bcnf decomposition is lossless, right? That's it. You can use, again, the way this decomposition was done is keeping each of these FDs or functional dependencies in mind using the Bcnf decomposition strategy, right? So it's a very simple, straightforward question. If you just know how to decompose using Bcnf, and if you know that Bcnf decomposition is lossless, this is like a 30 seconds question. Okay, cool. Let's go to the next question, folks. Okay, this is also not too hard, but it's an interesting question. This requires a little bit of thought process, but it's a very good. I like this question when I was solving it. Again, try to use that set theory type concepts, set mappings. I mean, that's what helps me. I mean, that's what I use every day when I have to solve FD questions. Please think, please think. Don't jump to an answer. Look at all the 4 options given to you. You have to read the question, folks, and the 4 options carefully. Yeah, I think most of you are getting it right. That's good to know. Good. All of you have thought through good. You've read all the options. That's important. Good. So obviously 4 is the right answer here. Again, it's very easy to visualize it. Look at this. You can write A determines BC as 2 FDs. You can write it as A determines B and A determines C. Now the way I was trying, our team of mentors writes these questions, and I try to solve it at least a few hours before the live session and try to correct it, take their feedback and stuff like that. So the way I have solved it is as follows, and I really enjoyed that process. So I can draw this diagram here, and A determines B and A also determines C. So I try to draw a graph-like structure here. Right? I mean, this is a very interesting way that I felt is interesting to understand. Now we have B determines A, right? So given B, I can determine A. That's what this graph looks like. So B also determines C. So I can also draw this. Now C determines A. So C determines A. Okay. C also determines B. Now if you look at this graph, one thing that you will notice here is from any vertex to any other vertex you can go in this graph. Right? You can go from A to C. So from this you can derive A determines C, or you can determine. So this graph is one way to imagine all of these functional dependencies in a diagram. Right? If you notice, you can go from A to C, which means A determines C. You can go from C to B, so which means C determines B. You can go from B to C also. Look at this. You can take this path B to A to C, which means B determines C also. Right? So this is one way you can visualize all of these stuff in one place. Now let's take this first. Okay. I mean, this is an approach that I felt interesting. Let's see. So you have A determines B, B determines C, and C determines A. That's what is your F dash in option 1, right? Now even in this graph, you can go from any vertex to any vertex because it's a cyclical graph. It's a graph with a cycle. So I can go from A. So from this I can determine that A determines C, C determines B, B determines A, and all of these things. Yes, you can also, as somebody rightly pointed out, as Anshuman pointed out, you can also use canonical covers. But that's a very standard approach. That's certainly a very standard and a nice approach, no doubts about it. I'm just exploring and introducing you to a slightly different concept. Certainly canonical covers is the standard textbook approach. This is something that I experimented and figured out while playing with it, right? So from these, again, by converting this into a graph-like structure here, think of it like an alternative way of thinking about the same thing, using concepts in discrete mathematics like graphs, right? Again, you can solve the same thing using canonical covers. I'm not denying that, right? This is just a new way. I wanted to introduce a new way of thinking, okay? Or approaching problems like these. Again, it may not work always, but it's an interesting way to think about it. So now let's look at this. So here also, from any vertex or from any attribute, I determines C, C determines B, and B determines A. Again, here also you have a cyclical graph. Again, by using this, you can easily see that you can derive any attribute from any other attribute, which is what this graph is all about. That's the essence of this graph, right? So you can see that this is right, this is also right. The moment you have two options being right, then all the above obviously fits the bill. But you can also look at it from this perspective. Okay, let's look at this from this perspective also. Here you have A determining B. Again, graph, right? If you look at this graph, you can go from any vertex to any other vertex here. Right? You can go from A to C, you can go from C to A, you can go from B to A, you can go from B to C. Everything is possible. So this is another way of imagining this, right? So you can use closures, but since everybody knows about the closures, I want to introduce a slightly different technique. Okay, this is sometimes useful, not always, but I was trying to take you to how you can map at least some problems in functional dependencies to a graph theoretic structure. Okay, again, this is my personal way of thinking. I have not read it in any book, but I find it interesting. Okay, so again, canonical forms, it's straightforward, very simple for you to, I am assuming all of you know it. We've also seen it in in the past videos, right? Sorry, in the past examples. So just wanted to introduce a new technique here. Cool. So let's go to the last problem. Is this visible or shall I make it slightly larger? So let me just make it slightly larger, the font size. Just give me a second, full screen. Okay, cool. Dismiss. Again, please read all the 4 options. I think this is the last question of the day. Okay, some of you are putting in the answers. Good, good, good. Good. Okay, so most of you got it right. Option D is the right option here, and it's very simple to observe. Right, so let's look at it. Only A. Obviously, that's not right, because if you look at it, when A is 1, B is 1, and B is also 4, which means A cannot be the candidate key, because given A, you can't uniquely determine B, C, D. So obviously, this option is wrong. Now, let's look at AD. You can write a structure like this, AD and BC. Let's write AD values. AD values are 1, 1, 2, 2, 1, 2, 2, 2, and 3, 1. Right, so those are the 5 options that you have. Now let's look at the corresponding BC values. The BC value corresponding to this is 1, 1, which means you can uniquely determine as of now. For 2, 2, it is 3, 4. For 1, 2, where is 1, 2? For 1, 2, it is 4, 1. For 2, 2, it is 3, 4. For 2, 2, it is 3, 4, right? So this, okay, that is okay. So given 2, 2, you are uniquely determining 3, 4. So that's perfectly okay. What about 3, 1? So given 3, 1, you get 5, 3. Cool. So AD uniquely determines BC, right? And you only have ABCD, right? So obviously AD is a candidate key. Here also you have AD. Now you have to similarly, using similar structure, you just have to see that, again, similar approach, same approach, just draw this set type diagram, right? Very simple set type diagram. And you create this CD, and you take this CD into, again, similar diagram you draw, and you'll see that you get, for every unique value of C and D, you get unique values of A and B. Similarly, for unique values of A and B, you'll get C and D, right? So this option is right and this option is right. So obviously option 4 is the right option, right? Again, somebody is asking us, why is this medium and not easy? Good question. For 2 reasons. One, there is this small trickiness where people might just jump to option 2 and not read through all of them. So there is a small trick associated with it, number 1. Number 2 is similar questions in GATE have been asked in the past, which are considered medium hardness. Again, this label of easy, medium, hard are all based on GATE, right? Again, as somebody rightly asked us, can we create slightly harder questions? Certainly we'll do it. Intentionally, we are not giving hard questions. Please understand that simple fact, that this is the first iteration 1. We will cover subject 1, subject 2, all the subjects. There are about 12 subjects or so. The way depends on how you group the subjects. In the first iteration, we will focus on easy and medium problems. We are hoping the first iteration should be over by late August. Hopefully by end of August, we'll try to finish the first iteration. From the second iteration, right, we will do whole subjects in probably 1 session or 2 sessions. Here we'll again go to, again here you have a rough spread of about 70%, about 60-70% easy and about 30 to 40% hard medium questions here. So later on what we'll do is, we will make medium level questions as the majority. We may completely skip, or we may have a few easy questions, but easy questions will be 20%, medium questions will be 80%. Right? So in iteration 3, we will do the other way around. We'll have medium and hard. Hard questions will be 50%, medium questions will be 50%. There is no point in preparing too hard questions for GATE. We are hoping that before the exam, we can do at least 3 iterations, but we'll try to do the 4th iteration also. Okay, in iteration 3, we can group subjects, right? So that's our plan. Again, we have done this earlier also, that we have created, okay, for example, in some of our earlier topics, right? We gave mostly medium and slightly on the harder side questions. Then students started panicking. They're like, I mean, we don't want students to panic. We want students to gain confidence through these exercises. That's why we are giving, again, these are also, iteration 1 is primarily for revision and gaining the foundational concepts. Iteration 2 and 3 and 4 will be more focused on problem solving. This is primarily for revision with mostly easy and a few medium questions. And we also want students to gain the confidence in these sessions, right? Because if a student directly encounters a slightly medium to hard question, they lose confidence. There is no point in it. Okay. In the whole of education research and learning research that we have been reading, the recommended approach is start with simple problems, keep increasing the complexity over time. Right? That's a very, very important approach, and we're trying to follow that approach. Again, some of you might directly solve hard problems, but we have to take into account a vast majority of students who might not be able to solve all the problems right away. Okay, that's the whole idea here, folks. Thank you very much. Next session, we'll announce it tomorrow. We will put out a video on Sunday, or mostly by Sunday, we'll put out the video about the next 2 live sessions, the topics and the subjects. Okay, so we'll put it out. We'll regularly do 2 sessions per week, as we have already told all of our students that we would do that. Okay, see you next week. We'll do an announcement video soon. Okay, so we'll try to do it on Wednesday. We're just trying to we'll do an announcement. Please bear with us. Typically we do it on Wednesdays and Fridays. This week we couldn't do it on Wednesday, and we could only do it on Friday. Right, we'll stick to the same pattern, but I'll make an announcement. Okay, thank you, folks. Thank you very much. Thank you for joining. See you next week. Bye bye.